Thanks everyone for being here and for taking interest in Nethermind's bounties. Here I'll briefly discuss the 4 of them, but I'll focus on zkML. So I'll speak about zkML first, and at the end I'll briefly mention the other bounties and point you to people in our team that you should speak to for more information. Okay, so our zkML bounty has to build a project that combines zk technology and machine learning. And of course, this is a very open-ended description, so let's look at some possible approaches that you may take to this bounty. So zkML, technically, we use the term zkML to refer to any application that uses zk technology in combination with machine learning or AI. So here, by zk, we don't specifically mean zero knowledge. We mean succinctly verifiable computation or zero knowledge. So we don't really care. It is possible that we don't have actual zero knowledge and we only care about succinctness. So that's perfectly valid. So zkML is a wide area of research and engineering. Some of these areas that I think are very interesting, at least for this bounty, are proof of correct inference, proof of training, and federated learning. So let's see, what's proof of inference? So in proof of inference, we have a model, let's call it F. And let's say that this model is signed by a trusted party, and let S be the signature. So in proof of inference, there is a public input, X, and one wants to create a zk proof for the following statement. One wants to prove that there is a model that has a valid signature, and that when run on input X, okay, so here it should say X. So when run on input X, the model's output, f of X, satisfies some property. For example, f of X is bigger than 0. So this is a bit abstract, so let's look at an example. So say that F is a model that takes a face photo and determines if the face corresponds to a legal citizen of the country. And S is a signature of the model that is made by the government. So now Bob could check that Alice is a legal citizen by checking that S is a valid signature of the model and running the model F on a picture of Alice's face and checking that the output of the model is, say, positive. Okay, yeah, so this is exactly the copy of the example. However, you could do that, but this means, for example, that every time that Alice wants to prove that she's a citizen, the whole model needs to be run. So Bob needs to run the model over and over again. So if Alice wants to prove that she's a citizen to several parties, then each one of the parties has to run the model. So an alternative could be that Alice creates a succinct proof of these 2 claims, that valid signature and that F, the output of the model, is positive. So it creates a succinct proof, and this way, whenever Alice wants to prove that she's a legal citizen, Alice just sends the proof, a picture of her face, and the signature. And then Bob just verifies that the proof is valid. So that's a typical use case of proof of inference. This is, for example, how WorldCoin wants to use zkML. So yeah, so in WorldCoin wants to do precisely this. And in here, S would be a signature of WorldCoin. And note that Bob doesn't even need to know the model. It just needs to know that it is signed by a party it trusts, like a government. Okay, so yeah, here we only care about pi being succinct. Here we don't really care about zero knowledge. We don't want to hide data here. Here we just want that the proof is short and that it can be verified very cheaply. And yeah, depending on the application, maybe F is not signed, it's committed, maybe F is public. Yeah, so, and this branch of zkML is currently a very hot topic of research and engineering, so I highly encourage you to take a look at this one if you are interested in zkML. So in then there's another branch of zkML, proof of training. So in proof of training, there's usually a private data set and a model. So I denote the model FWX. So here X is the input to the model and W are the parameters. And in many applications, you have a commitment to the dataset and to the model, or to some of them. And recall what does training mean? Training a model on a dataset D means finding parameters so that when you use these parameters on the model makes good predictions on this dataset. So the goal of proof of training is to create a zk proof of the following statement. I know a dataset D whose commitment is some public value, and I know some parameters W such that the model with those parameters commits to some public value. And these parameters are the result of running certain training algorithm for the model on the dataset. And yes, so this is exactly the end of the last slide. And why would we want to prove this? Well, there are several interesting use cases for proof of training. There's distributed training, where a model owner distributes the training of the model among untrusted workers. So there are several untrusted workers. You want them to train your model. So you ask them to train the model and also provide a proof that they trained it correctly because you don't trust them. So you could create some kind of marketplace of trainers. Or, for example, arbitraging copyright claims, where a model owner proves that the model was trained on data that doesn't contain copyrighted data. Okay, so yeah, proof of training is quite a tricky area of zkML, and this is because, as you know, training a model is orders of magnitude more expensive than running a model. So, just proving proof of inference is already quite a tricky area of zk. It's quite hard to do efficiently if the model is large. So proof of training, for example, large language models is sort of out of reach at the moment. So this track of this approach to our bounty is kind of more difficult than proof of inference. But yeah, if you want to focus your project on proof of training, that's perfectly fine. We will take into account that this is a harder aspect, that this is harder than proof of inference. And yeah, if you want to do this, I recommend you focus on small models, that you prove training of small models. Perhaps classical models instead of deep learning models. Or if you want to work on deep learning models, then just use models with a small amount of parameters. Okay, so proof of inference, let's go back to proof of inference and some ideas on how you might tackle this topic. So I would recommend you look at existing zkML solutions and improve some parts of it. In the bounty description, we have several links, and one of the links is awesome zkML. It's a GitHub repo maintained by Wallcoin, and there's lots of zkML solutions in there. So one possible way to start the project is to check those and look at one of them and try to improve a small part of it. So possible aspects of zkML that I think need improvement and that at Nethermind we are working on improving are the following. The treatment of floating point arithmetic, the fact that models in deep learning are self-similar, I'll explain what this means in a moment, and the fact that there's many non-linearities in the models. And yeah, now I will talk about these 3 points, but a very important point, if you want to work on this bounty, be creative. The best thing you can do for the bounty is to be creative and have a great idea, even if, yeah, so creativity is gold, so don't limit yourself to what I'm saying here. If you have nice ideas, please pursue them and surprise us. Okay, so one area of improvement, I think that it's low-hanging fruit for zkML is leveraging the fact that models are often the result, the computation of a deep learning model is often the result of applying the same computation many times, over and over again. For example, in a deep learning model, there's maybe a layer, like say a convolutional layer that's applied dozens of times in a row. And even, for example, in a single layer, there's many computation, the same computation that's repeated many times. For example, a convolutional layer applies the same filter many times for many patches. So it applies the filter to lots of patches of the input, right? And the same, matrix vector multiplication can also be split into chunks of computation where each computation is the same. And a popular technique to approach computations where this happens, that computations that can be split into smaller computations that look the same, is to use folding. So in a folding scheme, just a crash course on folding schemes, there's a prover and verifier. The prover has two statements that wants to prove, and then the prover and verifier interact to create a new statement, so that if this new statement is valid, then the two initial statements were valid. So in more plain terms, a folding scheme reduces the task of proving two statements to the task of proving a single one. So you can use folding schemes to prove large statements. So say that XW is the large statement. You can break this large statement into very small parts, each one from the same relation. This means that it's basically the same computation. And then you fold all these small parts into a single one, and then you prove the folded instance. So I think that zkML is ready for this type of technique. What's the time? 5 minutes? Okay, so let's look at this one, and then I'll skip the later point, and we can discuss after the talk. Okay, so deep learning models deal mostly with linear operations. Most operations happening in a deep learning model are inner products or matrix multiplications. However, there's crucial nonlinear operations happening in the models, such as ReLU, softmax, max pooling, etc. And proving this in a ZK snark can introduce a huge computational burden, because as you know, ZK proof schemes rely on proving statements about field operations, additional multiplication between field elements. However, ReLU and softmax, max pooling, etc. have nothing to do with field operations, and writing these nonlinearities as additional multiplications between field elements leads to a huge blowout in the statement you are proving. And yeah, a popular way to tackle this problem in general, not only in zkML, is to use lookup arguments. When you want to prove something that's very hard to arithmetize, you can use a lookup argument. This is already being done in some zkML applications, but I think it can be done in a much more deeper way. So if you want to know more about this, please come talk to me afterwards. Okay, so I'll skip this explanation of lookup arguments. Yeah, and so yeah, that's my overview of this bounty. As I said, please talk to me if you are interested in working on zkML. I'll be very happy to expand on any of the points I mentioned. Our other bounties are the following. Security-driven development. In this the goal of this bounty is to design, to develop some cool code and focus on how to make sure that the code is secure. So here we suggest you either use fuzzing or formal verification. Then another bounty is large-scale compute. In this bounty, the goal is to leverage L2 rollups where fees are cheap, so as to build an application that's not possible to run on Ethereum, an application that uses a lot of computation. For example, some game that requires a lot of computation, or maybe training models on Starnet, for example. And then preconfirmations innovation, anything that has to do with preconfirmations, even if it's just a theoretical exploration, is welcome in this area. for if you are interested in any of these bounties, please come talk to us in our stand. And yeah, as final remarks, we are hiring. So we are both hiring for full-time positions, and then we have a wonderful internship program. Yeah, if you are interested in working with us, if you want to work on any of the topics I just talked about right now or many more, please reach out to us, and please reach out to Aya in the back of the room. Thanks.